Hi everyone, welcome to this lecture on extensions of linear models. After talking about linear models in the previous lecture, I'm going to go over the assumptions of the linear model, and I'm gonna explain how each assumption plays a crucial role and what to do if those assumptions are not satisfied. The assumptions made in the previous chapter have consequences on the properties of the OLS estimator. If you remember, I talked about consistency, I talked about unbiasedness, I talked about asymptotic normality, and I talked about best linear unbiased estimator, blue, the blue property. So we're going to challenge each of these assumptions and look at the implications. This applies to linear models in this case, but in general, every time you have to think about a method, an econometric procedure you want to use to answer a question, you will have to think, okay, this works under these assumptions. Are these assumptions verified? Yes, no. What are the ones I can verify? What are the ones I can only argue in favor of or against? And what are the ones that seem to definitely not be satisfied? So I have to find other estimators and alternatives. And so, because we are going to challenge these assumptions, we are going to talk about alternative estimators. So, the outline of the lecture is pretty much going through each assumption, see what the implications are, and see what to do when they are violated. The first assumption was the linearity assumption. The second assumption was the i.i.d sample. Then I talked about exogeneity. I said the expectation of the error term conditional on the regressor or the covariate is equal to 0. Then I talked about no collinearity. I said pretty much that two x variables are not proportional to each other, and I will extend that definition of collinearity. And finally, the last one was the homoscedasticity assumption. This one in particular was required for the OLS estimator to be the best linear unbiased estimator, to be blue. Okay, let's jump right in. So, assumption 1 was the linearity of the regression equation in the parameters. Remember, here what's important is not that y is linear in x, rather that y is linear in beta 0. So for instance, if you take the model yi equals beta 0 plus beta 1 xi plus beta 2 xi squared plus epsilon I, this is also considered a linear model, because even though I take the square of x, as long as beta shows linearly, we are in a linear model. If beta, for instance, shows up as a square, as an exponential, as an inverse, or anything like that, then we will be in the case of non-linear least squares. The properties are a bit different, and this estimator is not as used, because if we can justify a model with a linear relationship, we would do so. So a nonlinear relationship in the parameters would be used only if we cannot do otherwise. Remember that very often imposing linearity on a model or assuming linearity is a shortcut. It's an approximation. There is no real relationship in real life which is perfectly linear, more or less. So what we do is we approximate this nonlinear relationship with a straight line. Hopefully, this approximation is good enough. There will be some error due to the fact that we are using an approximation and not the true relationship. But at the same time, linearity also buys us some appealing properties that will offset this irreducible error due to the approximation. I talked about last week I talked about some variables which are some x's, which definitely are not don't have a constant effect or constant marginal effect on the response variable y. I talked about typically age or experience that seem to have a quadratic effect on earnings. That was only one example among many. I said pretty much that one additional year of experience does not increase your wage the same way, depending on whether you are very experienced or very inexperienced. Data suggests that past a certain number of years of experience, the earnings, wage, does not increase as much as when an employee is in his younger years. There are different reasons to that, of course, in real life. You can think about the fact that young employees tend to be more dynamic. They tend to train themselves. They tend to take more opportunities. They tend to maybe work extra hours at the beginning. You know, they can have an ambitious career. They want to do well. They want to get promoted. So they show more effort, which will also translate into an increase in their wage. More senior workers, after 45 years old, I'd say, might not be as dynamic as younger employees. They have families to take care of. They might be more keen to work a fixed amount of hours every day, being done at 4, 5 p.m., 6 p.m. every day. They might not be able to travel as much for business purposes. They might not want to. And so we might not see such a big increase in their wage as they keep working. But if you take the other example, xi prime beta 0 square, that pretty much corresponds to beta 0 plus beta 1 x1 plus beta 2 x2 square, is not a linear model. This is due to the fact that in this equation, the coefficients, the betas, will show up sometimes linearly, but also sometimes with a square on them. The properties of the non-linearly squares estimator are a bit different, and this is not something I will talk about in length in this lecture or in this course. Remember that linearity is also assumed because it has appealing interpretation properties in terms of marginal effect. You increase x by 1, y increases by beta 0. Moving to a non-linear least squares model would make interpretation more difficult. Now, as I said, this assumption is, in general, wrong. But it can be wrong in various degrees. It can be slightly wrong in the sense that the relationship looks pretty linear, so we won't lose too much by assuming it. But other times, the relationship could clearly look, or maybe a model could back up your story, and it would look highly nonlinear in the parameters. In this case, a linear model will induce a high approximation error. So I suggest in general to visualize your data to justify your assumption. If you have more variables, let's say 20 variables, 30 variables, 1,000 variables, it is way more difficult to visualize data on a graph because graphs only represent 2 dimensions, maybe 3, if your software can do it. So let's illustrate those nonlinearities with an example. I draw a sample of size 500, but my dependent variable y is not a function of x1, rather it is a function of x2, and x2 is the logarithm of the square of x1. I took the square to make sure x1 is always positive, because the logarithm of negative numbers doesn't exist. It's not defined. And then I defined y as being my log of x1 squared plus a narrow term, which is normally distributed. Note here that the coefficient in front of x2 is going to be a 1. So here my beta 0, the true coefficient, is going to be a 1. This is what I want to estimate. Now, imagine that instead of looking at the relationship between y and the log of x1 squared, I look at the relationship of y and x1. What's going to happen is, if I plot my data, if I plot y against x1, I will get this scatter plot, and clearly fitting a linear model through it will lead to highly inaccurate predictions for most of the values of x1. If you fix x1 to, let's say, 0, here the true regression function shows you something around here. However, your prediction is going to be way far off because you're going to have to look at the corresponding value on the straight line. Any very low value of x or very high value of x will also yield very inaccurate predictions. This is because we are approximating a highly nonlinear relationship with a straight line. So, if you're interested between the relationship between y and x1, you can plot the data and see if at least the relationship looks linear somehow. Clearly here, the scatter plot shows that this is not the case. Now, if somebody knows the relationship between y and x, and somebody knows that y is not related to x1, but rather to the logarithm of the square of x1, then one can fit a regression by taking the log of the square of x1. And if you do, and if I make the regression of y on log of x, or log of x squared, sorry, and I plot this relationship, here at the bottom we have x2, then you can see that now the relationship looks very linear. In fact, if you look at roughly the coordinates of the points are all centered around the 45-degree line. If you take this point here, this is the point -5, -5. When x2 is equal to -5, xy is also equal to -5. That shows that the slope of this relationship is indeed close to 1. We estimate it. We estimate something slightly over 1. You can see here that if it was exactly 1, it would be at each intersection. It is slightly above every time. Probably something like 1.1, 1.2. But this approximation is good because the true relationship now is linear. Your predictions won't be very far off. Any questions about linearity? Okay. Assumption 2 is about having access to an i.i.d. sample. An independent and identically distributed sample is available. We have some x's, could be a vector with many covariates, a response variable y, and we have access to a sample of size n. The idea of independent and identically distributed is that the x's and the y's of Mr. 1 are independent from the x's and the y's of Mr. 2. Moreover, they are identically distributed. They come from the same distribution. They are two different realizations of the same random variable. A case where this assumption will be violated is if you look at some family data. Imagine that you look at some variables within the members of the same household. So you have a household 1 with 4 members, and you have their observations. Then you have household 2 with 4, maybe 5 members, and you have the corresponding x's and y's. Chances are that the x of one member in the household could be correlated with the x of another member in the household. This could potentially create problems. This assumption is the kind of assumption which is realistic and easy to defend if one knows the conditions under which the sample was obtained. This is why it is very important to look at the details, the description of a dataset when downloading it to perform some analysis. Just because of the way data is being collected, your results could be drastically different. So you have to be very careful about how things are recorded. Sometimes things are recorded sequentially, like a panel survey. You ask people to report some data every year, or maybe every 6 months. So then there is a time dimension to the dataset. In this case, it will make more sense to regress a variable observed today on a variable observed today or yesterday, as opposed to regress a variable observed yesterday on a variable that was observed later. Without this assumption, the OLS estimator might be consistent and unbiased still, but it requires more technical assumptions for laws of large numbers to apply. This is something I haven't talked about in length. The law of large numbers, the laws, there are several, are extensively used to show consistency and asymptotic normality of the OLS estimator or of estimators in general. Those laws in particular require data to be i.i.d. If data are not i.i.d, then different laws of large numbers can apply, but they are more technical and the proofs are more involved. So generally, one prefers to use i.i.d data because once we know the data is i.i.d, we don't need to be worried about assumption 2 anymore. We know that all of the important statistical theorems will apply. Law of large numbers and central limit theorems in particular. Any questions about assumption 2? Okay. Assumption 3 is very, very important. It is an assumption that typically fails, and there are many ways to show that it could potentially fail, and it leads to a wide range of problems. So, assumption 3 was exogeneity. We assume here that the error term has an expectation of 0 conditional on xi. So if we fix the value of the covariate to any value x, the error term on average is equal to 0. What happens if this is not satisfied? Well, it means that, roughly speaking, that xi is somehow correlated with the error term. The covariate is correlated with the unobservable error term. In this case, we say that x is endogenous, as opposed to exogenous when this assumption is satisfied, hence the name exogeneity. If x is correlated with what we do not see, then it will bias our coefficients. The idea being that the x you observe is correlated with something else that we do not observe. So the effect of x on y will also be affected by the effect of epsilon on y. If epsilon, one way or another, is related to x, when x changes, the epsilon would change as a result of that. And the effect on y will not only be attributed to xi. It could happen for many reasons, and the most common reason is omitted variables. Remember that epsilon is everything we do not observe. Everything but the x's. So if there is a variable that we do not observe, which is correlated with x, then we are in trouble. As a consequence, the OLS estimator is not unbiased anymore. But if it was only that, that would not be a big issue. After all, except the OLS estimator, most estimators are biased. As long as they're consistent, we can just find a big enough sample so that the bias will be negligible. The problem here is that if x is endogenous, the OLS estimator is biased and it's not consistent. It does not converge to the actual coefficient in front of x. Rather, it's going to converge towards the coefficient on x plus another term that we do not observe. This other term will contain the correlation between the error term and x. So, OLS is not reliable anymore in this case. Simply not reliable. How can we estimate beta 0 in a reliable way? There has been a lot of research on this problem, myself included. I've done some of my thesis on endogeneity problems. And since the 1920s, a way to solve the endogeneity issue is to consider a variable z, which is a third kind of variable, that has two features. The first feature is that this one is exogenous. The error term, on average, is equal to 0 when we fix z to any value. The second property of this variable z is that z is correlated to x, but does not directly affect the variable y. So it has to be correlated with the endogenous variable, but it should not be directly correlated with the response variable. The idea is that we're going to use z as a proxy for x. Since z is correlated to x, when x moves, z will move as well, or the other way around. And we can use that to look at the effect on y. But we need z not to affect y directly. Z should affect y only through x. In some sense, we're going to use z to represent x while being exogenous. In this case, z is called an instrument. Now, how do we get to a final estimate? How do we obtain a good beta hat with this z? The procedure works in two steps, and this is why it is dubbed two-stage least squares estimator. at each step, we are going to run a regression. The first one is to regress x on z. So we observe both x and z, and we regress x on z. So instead of using y on the left-hand side, I'm going to use x. The idea is that x and z are correlated one way or another. So I can predict x in a reliable way if I use z. So I'm going to use this regression to make predictions of x, but those predictions are only based on z, which is exogenous. So these predictions, x hat, they are exogenous. X alone is not, but x hat is exogenous because we build those predictions only using an exogenous variable. Once we gather all of these predictions, we can go on to the second stage. We regress the variable of interest y, not on x, but on x hat, on the predictions of the first stage. Because now we are regressing y on an exogenous variable, which is somehow close to the true endogenous variable x. And I say somehow close, I mean that the predictions should be relatively good if x and z are correlated. The predictions will never be exactly the number x because they will take the endogeneity out of the way. X hat is free of any correlation with the error term. The resulting estimate, which I'm going to call beta hat 2 SLS, two-stage least squares, is consistent and is biased. Do not worry too much about the bias. Again, OLS is the only unbiased estimator I know, more or less, I believe. But it is unbiased when it works. And it works when the assumptions are satisfied. Very often, you won't be able to satisfy all of the assumptions for the OLS estimator to perform well. At least with beta hat 2 SLS, we can gather a sufficiently big sample for our estimates to be reliable, even though biased. Remember that consistency is the same as asymptotic unbiasedness. The bigger the sample, the lower the bias. And eventually, when it goes to infinity, the bias shrinks to zero. And this is why the only thing we have left is the actual coefficient beta 0 we are trying to estimate. This is not the only estimator that uses instruments. There are many more. For instance, I made one where the predictions are not obtained via OLS, but they are obtained through another method. In general, we call any estimator that uses instruments instrumental variables estimators. Now, because of this omitted variable bias and because of the potential problem of endogeneity more generally, when you gather data, you want to have as many variables as possible to reduce the omitted variable bias. The more x's you have, the less correlation you should get between epsilon and x. And at the same time, some of these variables could be used as instruments. It will look like they don't make sense to predict y, but they do make sense to predict x. And this is a good property for an instrument. There has been a lot of research in this area, and nowadays it's more or less saturated. it's not really trendy anymore. In particular, there has been a lot of research on what to do if the correlation between x and z is actually not that big. In this case, we would say that z is a valid instrument because it is exogenous, no problem with that. But because its correlation with x is weak, we would call this a weak instrument. Because of this weak correlation, we can get into another plethora of problems. There has been a lot of research on how to solve that problem when this is the only thing we have available, when we have only y, x, and z available, when we don't have strong instruments pretty much. Let's see how it looks in R. So, I created a sample of 100 observations. I created a variable z. I created my epsilon, my error term. And then I created another error term called v, so that I'm building my variable x as a function of z, because I want some correlation, as z plus some error term v, but it also contains epsilon here. This means that x depends on epsilon, but epsilon is the error term that also shows up at the end of the main regression equation. Because x and epsilon are correlated, the OLS estimator is not going to produce good results. And I'm going to show you in a couple seconds. Forget about sigma. This has nothing to do here. I don't know why I have it here. I have beta 0 as an intercept equal to 1 and the coefficient on x equal to 2. So y depends on x and on epsilon, but x depends on z, on epsilon, and some random noise. The random noise v is nowhere else. If I make a regular linear regression of y on x, so I estimate the coefficient by OLS, this is what I get. My intercept, which the real one is equal to 1, my estimated intercept here will be equal to 1.07. Not bad for a sample size of 100. It's a rather small sample size, so I cannot complain. However, the coefficient on x is equal to 2.3. 2.3 is pretty far from 2. At this stage, you might be thinking, wait a minute. Is it just because I have a very small sample and I need to wait and I need to increase my sample size if I want to see more accurate results? Or is there something going on here? This 0.31789 is a pretty big number. So maybe there is some endogeneity going on. Let's see. If I consider a big sample instead, I do exactly the same procedure as above, but instead of 100 observations, I can create, let's say, 1,000, 10,000, a million. You can see that my estimate of the intercept has gotten better. I had 1.0 something before, now I have 1.00. I'm getting closer to the true number, which is 1. However, the estimated coefficient on x is at the same magnitude as it was before. I had 2.31 before, now I have 2.339. My sample is bigger, yet I am not any more precise. This comes from the fact that x is endogenous. In fact, between those two regressions, there seems to be a difference of 0.3 above. So the OLS estimator overestimates the impact of x on y. It estimates more than it should. Why does it estimate more? This comes from the fact that epsilon and x are positively correlated. The bigger the epsilon, the bigger the x. And since y depends on x here, but also depends on x through epsilon, when x increases by 1 unit, it just doesn't increase by beta 0, it also increases through epsilon. So this 0.3 here is a measure of the bias or the omitted variable bias. Well, in fact, here it's not really omitted. We have x. It is just due to the fact that x and epsilon are correlated. It is very common to find endogeneity like that in problems such as the effect of schooling on earnings. I talked about this before for the effect of experience on your earnings. But if you look at the impact of years of schooling on the wage, well, you will find a lot of variability. Many people spent 5 years in college, but not everybody is getting paid the same. This could be due to, for instance, the type of degree, sure. The type of firms you're working for, sure. But if you take those X's into account, you might still get a bias. Why do you think that is? The bias could come from the fact that there are some things in people that we just do not observe. It's embedded in epsilon, but it's related to X, to the number of years spent at school. Why is that? Because students, or people in general, make a decision. They decide to get a bachelor's degree. They decide to get a college degree, a master's, a PhD, or no degree at all. This is something they decide based on their personal preference, based on their personal ability, and based on many other factors. A lot of these factors cannot be observed. Ability, intelligence, gift is very hard to measure. IQ tests are only imperfect measures of intelligence. Somebody with an IQ of 160 or more might not get paid well because he just doesn't know how to behave in the firm. Maybe he doesn't know how to seize opportunities. He might be very smart, but doesn't know how to communicate about it. The choice of going to college or not, or how long do I go to college for, what kind of degree do I want to get, in what major, will be a function of your natural ability. Oh, I always did well in STEM courses, so maybe I'm going to do an engineering degree, or maybe I'll get a math degree or physics degree. Those things are not observed, and they will be correlated with your choice of years of schooling. So, automatically, if you decide to spend 1 more year in school, the effect on your future earnings is not just the effect of 1 year of schooling, but it could be the effect of many other things that we don't observe. It is a very popular regression equation, estimating the impact of schooling on your wage. There have been many different propositions about how to estimate the coefficients in a consistent way, in a reliable way. And to this day, there is no one single best way to do it, but it has improved a lot over time. Now, what happens if I use my new estimator, the 2-stage least squares estimator? A package called AER allows me to use a function called ivreg. So this is a way to just call the function that comes from another package that R doesn't have by default. It is something you have to download through R. It's a bunch of codes that have been created by other researchers that you have to download and then that you can use. The first part of the formula is the same as the previous function I used, lm. It's like making an OLS. But then you make a vertical bar, and here you put the instrument that you are going to use in place of x. I used some data called data where I have y, x, and z, the ones I made here. And R understands that it needs to perform the two-stage least squares estimator with this data. First, regress x on z, compute the predictions x hat, and then regress y on x hat. In fact, you can do it by hand. You can use the lm function twice in a row. Use it once where you regress x on z. Then you ask R to return the predictions. You call them x hat. And then you make a second regression using lm where you regress y on x hat. You can check that at home. It will give you exactly the same result as here. Now, the data set I used is exactly the same as this one. I have 10,000 points, which is a pretty big sample size. And my data is exactly the same as what I made here, except that here I have 10,000 instead of 100. We went from 2.33 in the OLS case to now 2.01. It is good. It is way closer to the real number, the true number, which is 2. You can see that the intercept is consistently estimated again, 1.003502, 1.004387. Qualitatively, those two numbers are the same. Note that although I have a sample size of 10,000 observations, I still have a number here. I only have 1 0 after 2. This is due to the fact that the two-stage least squares estimator is biased, and the correlation in my case, the correlation between the error term and x is actually rather strong. So this bias still remains a bit, but if you want to try at home and put 100,000 observations, then you will get into double zeros here, and you will reach better precision. Note that this method adds variance to the coefficient estimates. The standard error here is equal to 0.01, whereas in the previous slide it was 0.004. And it will always be the case. The idea is that by doing two different regressions one after the other, we are adding variability in the process. This extra variability comes from z, which we did not use before. We use z on x and then x on y. That's what we do here, as opposed to before using x on y directly. This additional variance will induce higher standard errors, so inference will not be as precise or as accurate as in the OLS case. However, the coefficients are going to be valid. A confidence interval made with the 2SLS estimator will be more reliable than a confidence interval made with the OLS estimator. Because of the bias, the confidence interval in the case of the OLS estimator will be centered around the wrong value. The real confidence interval might be here, but OLS will fail to get there, and instead they're going to get there. The 2SLS estimator at least will get you the right confidence interval, but it's going to be wider, less precise, but still centered around the true value of the coefficient. Any questions? In practice, if you have to do a linear regression, I strongly suggest you to think about ways in which X could be endogenous. If you are interested in X only, think about what could be correlated with X that I do not see. Chances are you are going to come up with something. Now, if you come up with something, you have two solutions. Either you think this correlation is very high, so the OLS estimator will not do, or you think, well, this correlation is not that high actually, so it won't be a big problem. My actual estimates will not be too far off. If, for instance, here I had 0.1 epsilon instead of just 1 times epsilon, the correlation between X and epsilon would be very small. And the OLS estimator will not return something that far off. It will return something like 2.1 maybe. So the OLS estimator might still be useful if the correlation between the error term and the covariate X is actually not that high. Just in case though, you should think about why there could be a bias and what kind of instruments you could use to estimate the coefficients in a reliable way. Imagine you are interested in the effect of 3 variables on y. If the 3 of them might be endogenous, then you are going to need 3 different instruments. In fact, you need at least as many instruments as you have endogenous variables. You can use more instruments than needed, no problem with that. It can in fact reduce the bias, but you will not be able to use one instrument for 2 different endogenous variables. Any questions? Okay. Why don't we take a break here? It's been almost an hour already. And resume the lecture in about 10 minutes, 3:35. Enjoy your break. Okay, I'm gonna wait for maybe 2 minutes. I just have to put sugar in my tea and I will resume. Let's resume the lecture. Is everybody here? Everybody ready? Any questions before I resume? Okay, let's go. So, after going through assumption 1, 2, and 3, let's now move on to assumption 4, no collinearity. This assumption states that the matrix gathering all the observations has rank k, or, in other terms, it is full column rank. Those are technical details that you don't need to really understand. What you need to understand is that this means that there are no x that can be expressed as a linear combination of the other x's. So, if this assumption is not satisfied, it means that two explanatory variables or more are linearly related. In this case, we say that those variables are collinear. Here is an example. Imagine we have a variable x1, a variable x2, and a variable x3. If x1 can be expressed as a times x2 plus b times x3, where a and b are two numbers, they can be positive, negative, doesn't matter, then x1, x2, and x3 are said to be collinear. This means that if you include those three variables in the same regression, it is going to be redundant. Because if you add x1, but if you add also x2 and x3, then x1 has absolutely no new information. x1 can be just expressed as a combination of x2 and x3, so x1 adding x1 on top of x2 and x3 will not bring any new information to the regression. You could also say it is redundant. What's going to happen in practice is the software is going to return a numerical error. Or, if it's not a numerical error, it will return very, very high standard errors because the software was close to getting a numerical error. In practice, collinearity is never exactly perfect like here, unless you design it to be so. So chances are that your regression will work and you will get very big standard errors. But in this case, you need to pay attention to the standard errors and wonder maybe some of these variables are redundant. It's just unnecessary information at this stage. The problem is that when you deal with many variables, and in particular, this is because we have access to many variables now that machine learning is so popular for big data problems, collinearity is more likely because you could find many possible combinations of some x's that would give you another x. So the more variables you have in your data set, the more careful you need to be about collinearity. You need to identify what each variable is and not throw them mindlessly. You have to wonder, oh, if I add the height of my observation in centimeter and then I have another variable that shows me the height in feet, chances are you're going to have numerical issues because of the conversion. Same if you deal with Fahrenheit degrees and Celsius degrees. 1 Celsius degree is equal to 32 degrees Fahrenheit plus 1.8 degrees Celsius. So the conversion is exactly linear. So whether you include Celsius or Fahrenheit will have the same effect on y. If you include both, that's redundant information. Only one would be enough. Let's see how this translates in the data. So again, I generate some data. I've got some x1 and x2, which are randomly generated normal variables. And I create x3 out of x1 and x2. 0.5 x1 minus 3 times x2. So x3 is what we call a linear combination of x1 and x2. Note that here, the linear combination is perfect. If you give me x1 and x2, I don't even need to observe x3. I can create x3 with my x1 and x2. I can perfectly predict x3 once I have x1 and x2. I could have added here a tiny error term, a disturbance, so that x3 is not exactly a linear combination, but close enough. And then I create my variable y as being x1 plus x2 plus an error term. Now, let's go through a couple of scenarios. First one, let's include all the 3 variables, which is why I call this 1, 2, 3 here. I regress y on x1, x2, and x3. What's going to happen is one coefficient will be not defined because of singularities. So R will be aware that there is collinearity, and one of the coefficients will not be able to be estimated. So, in this case, R will return a coefficient for x1 and x2, the first 2 variables, but not for the third one. Try this at home. Swap x1 and x2 here, or x1 and x3, and you will see that the last variable is the one that R will give you an NA for. Note that the coefficients on x1 and x2 are close to 1. Since in my model there is no intercept is equal to 0, this is also a pretty accurate estimate of the intercept. So, consistency is not a problem here. the problem is that one variable is being redundant. In theory, there will be consistency issues, but just in theory, to show mathematically that the estimator is consistent. What happens if you only include x2 and x3? Now, the coefficients on x2 and x3 are equal to 7 and 2. Remember that y was equal to x2 plus x1 plus the error term. 7 is very far from 1. Does this mean we are biased or inconsistent? No. Here we omitted x1. We did not put x1 in there. So the exact contribution of x2 on y is not equal to only 1. It's also permits through this relationship. So do not be surprised if when you remove one of the variables, the coefficients are going to change in values drastically. Because remember, in the background, we have a relationship between x1, x2, and x3. This relationship. In fact, this is something you could do in the full model. Replace x3 by those numbers. Put it there. And that would change the value of the coefficient on x1 and the value of the coefficient on x2. In fact, if you do it, you end up with 1x1 plus, imagine there is an x3 here, that would be plus 0.5x1. So the coefficient in front of x1 would be 1.5 plus 1x2 minus 3x2. The coefficient in front of x2 would be minus 2. That's if there was an x3 here. Now imagine I swap and I include x1 and x3. No x2. No problem in the coefficients. No error returned. No NA or anything like that. But you need to be aware that if there is such a relationship in the background, you need to be very careful. Here also, I did not include x3 as part of my initial regression, but I could have, and that would have changed the value of my coefficients. And finally, if I only include x1 and x2, this is the correctly specified model, because the initial model has x1 plus x2, no x3. So this is how y was built. Well, when I include x1 and x2 then, you can expect the coefficients in front of them, the estimated coefficients, to be pretty consistently estimated. 1, 1.00, and 1.01. In practice, there are ways to check for collinearity. In the book, Introduction to Statistical Software with R, ISLR, Introduction to Statistical Learning with R, there is a whole section on something called VIF. It is a formula including the R square when including a specific number of variables, and when the number is high or low, it is a sign of collinearity. In practice, I suggest you to look at that once you estimate your regression, just to make sure that at least you don't have any collinearity problem. It is not really the purpose of this course to study the linear model in length. I could make 3 more lectures about all the things around the linear model. I just want to quickly expose you to the potential problems, to teach you a way of thinking about why do I use this procedure over that procedure. Remember, every time procedures work because assumptions are made and assumptions are satisfied. If they are not, you need to move on to another procedure until you find a consistent one or a reliable one. Once you have that, you will be able to be confident in your results, and you will be able to present them in front of an audience. Remember that some of these regressions, some of these results might imply millions of dollars of expenses. If you work for the government and you look at the impact of a tax on unemployment, you want your regression to be pretty consistent, pretty reliable, because being off even by a couple of decimals will lead to millions and even billions of dollars lost in investment towards maybe the wrong policy. Any questions? Okay. Well, that's four assumptions down. Sorry, one to go. Let's move on to the last assumption. Homoscedasticity. Homoscedasticity assumes that the conditional variance of the error term does not change across observations nor with the value of the covariate x. So, if you fix x to a value small x, the variance of the error term when big X is equal to small x, which I call sigma square of xi, is in fact independent of xi. It is a number that does not depend on the value x can take. We saw that this was needed to make sure the OLS estimator is blue, best linear unbiased estimator. What happens if it is not satisfied? We also saw that consistency and unbiasedness are not affected by that. Whether we make this assumption or not will not prevent us from using the OLS estimator for estimation purposes. However, we're going to have a problem once we look at the standard errors, once we want to make test statistics, once we want to test some hypotheses, once we want to build confidence intervals. So anything related to the variance of the coefficients is going to change whether we make this assumption or not. So, if the homoscedasticity assumption is not satisfied, we say that errors are heteroscedastic. Homo means same, hetero means different. Hence, for instance, homonym, two words that sound the same. Or homosexual or versus heterosexual. It's a preference for the same sex or a different sex. Or the other sex, I guess. As long as assumptions 1 to 4 are satisfied, the OLS estimator, as I said, we're good to go. We can stick to OLS. However, it is not blue anymore. So once we test hypotheses and we make confidence intervals, we will not be able to use the regular OLS standard errors, the ones that show here. Those numbers will not be valid if the errors are heteroscedastic. The consequence is that confidence intervals produced by the OLS estimator are going to be narrower. Why narrower? Because OLS will always give you a small variance, a small standard error. At the end of the day, R doesn't know if errors are homoscedastic or not. When R computes the OLS estimator, you don't need to tell R whether errors are homoscedastic or heteroscedastic. The problem with that is that the standard errors used to produce confidence intervals will not be correct. They will not be the right ones. The standard errors will be smaller than the good ones, the valid ones, and that might lead you to wrong conclusions. The confidence intervals could be too narrow, and you might think that the true coefficient is somewhere down there, with the confidence of 95%, of course. Whereas in fact, with 95%, it might be in this interval. So one has to be careful about the standard errors and how to deal with them. So what can we do? First of all, let's talk about detecting heteroscedasticity. One can detect heteroscedasticity by plotting the residuals of an OLS estimation on the fitted values. You obtain the residuals, the difference between the actual data y and the estimates y hat. Those are the residuals. And you plot them against the actual predictions. So on the x-axis, you put the predictions. On the y-axis, you put the residuals. Visually, we will be able to tell whether there are signs of heteroscedasticity or not. If the residuals don't seem to change in their variance, then there is no evidence of heteroscedasticity. And I'm going to show you what I mean by variance of the residuals. If residuals display more variance for some values of the fitted values but not others, so for some predictions the residuals fluctuate a lot, but for others they don't fluctuate at all, then that will be evidence of heteroscedasticity. Let's illustrate that. I have a sample size of 200. I generate my x's, normal distribution, and I have this number sigma, which is my standard deviation for the error term. So if I leave sigma at 2 and I generate the error term with this variance, with this standard deviation, the standard deviation will be the same everywhere. So no problem, homoscedasticity. What I'm going to do, however, is I'm going to make a loop. I'm going to teach you how to make a loop later. And I'm going to create 200 epsilons, one by one. But each epsilon, each individually, will be normally distributed with the same mean of 0. On average, it's still equal to 0. But I'm going to change the standard deviation, SD. And I'm going to make it a function of the corresponding x. So for Mr. I, the variance of his, or the standard deviation of his epsilon, will be equal to sigma, which was equal to 2, times the value of Mr. I's x elevated to the square. Then I get my coefficients, beta 0. I get my response variable y. Is going to be an intercept plus the variable x with a coefficient of 2 in front of it, plus my error term. Now, I can fit a linear model without adding any heteroscedasticity assumption or anything like this. I will get the fitted values, which are also called predictions, fitted values. I get the residuals from my OLS model, my OLS object. And then I can plot. What do I see? Here I have 200 dots. Each dot is a prediction. I am plotting the prediction against the corresponding residual. For each prediction y hat, I have one residual yi minus y hat. Note that when the fitted values are between 0 and 2.5, all of my residuals are stacked around 0. As soon as I go lower than 0 and bigger than 2.5, then the residuals start scattering. And the bigger they get here, the more variance there is. They are super widespread, and same on the left. This is evidence that something is going on. The variance of the error term is changing when x changes. When you see something like this, you can start thinking, okay, I cannot make my confidence intervals the usual way. I have to use other standard errors. So, what are the possible solutions to heteroscedasticity? I'll go over 3 different approaches. It really depends on your knowledge of the variance of the error term. If the variance of the error term is fully known, what you can do is reweight xi and yi. So you multiply each x and each y by a certain number to obtain transformed variables xi star and yi star. This weight will be proportional to the standard deviation of the error term at for observation I. Imagine, for instance, that Mr. 1, the first observation, has a standard deviation of 3, but Mr. 2 has a standard deviation of 2. What you can do is reweight the observations of Mr. 1 by dividing them by 3, and you can reweight the observations of Mr. 2 by dividing them by 2. If you do this, the new error terms for each, for Mr. 1 and for Mr. 2, will now have exactly the same variance. So, by reweighting the observations, you go back to a regression where you have homoscedasticity. Once you're there, OLS. And now everything is perfect. You can look at the standard errors, no problem. This is what we call the generalized least squares estimator. So, as opposed to ordinary, we now say generalized because of the way the formula looks like. I won't show you the formula here, but this reweighting is pretty much going to change the values of x and y, and so in the actual formula, we see an extra term appear. That's the first case. Now, the second case is if the variance of the error terms is unknown, but the structure is known. We don't know exactly what the variances are, but we know the process they follow. What you can do in this case is consistently estimate the variance covariance of the error terms using the OLS regression. You can obtain the sum of square residuals, and then you can reweight x and y again by the square root of the estimated variance, which is the estimated standard deviation. So here I'm doing exactly the same thing as in the first case, except that I do not know the exact variance of the error term. If you can at least estimate this variance in a consistent way, for that I would need to know the structure. I would need to know, for instance, that the standard deviation is a number times x squared. If at least I know this, then I can estimate the standard deviation for each observation and again reweight. Once I reweight, I can run a second OLS regression using my new x star and y star. We call this the feasible generalized least squares estimator. the FGLS. Finally, the last solution is what we should use if we don't know the variance and we have no idea about the structure of the variance. So we cannot make any guess, actually. One can use the OLS estimator as before. As I said, the coefficients will be unbiased. It will be consistent, so at least I have reliable estimates. But since the standard errors are my problem, I'm going to change the way I compute them. I'm going to use another formula that accounts for heteroscedasticity. It is a formula that includes the fact that errors could be heteroscedastic. There are different estimators. The most used one is called the White heteroscedasticity consistent estimator. White is a very famous researcher in econometrics. He has done a lot of work. His name has been put on many different things. The most famous one is his heteroscedasticity robust or consistent estimator. The idea is that this formula is going to estimate the variance as before, but now the estimate is going to be consistent. If errors are homoscedastic or if the errors are heteroscedastic, in either case, once the sample size is big enough, our estimates of the variance are accurate. If they are accurate, I can use those standard errors to make to build confidence intervals or to test hypotheses. This solution is the one that is being used the most. The idea is that in the former two, we need some sort of knowledge about the error terms, about their variance. But once you get some data, because you're interested in some question, very often you have no idea about the structure of the variance of the error terms, let alone their value. So, since you don't know much and maybe you don't want to make wrong assumptions, because this will change results a lot, what you can do is use a formula that takes into account the possibility that it is going to be heteroscedastic. And if you look at, once you get to read papers for the course, for the presentations, you will see that everywhere there are linear regressions, most of the time, under the table of results, they will report that the standard errors are, they will say heteroscedasticity robust, or they will call Aker-White standard errors. They will use something like that, some adjustments. What is nice about this adjustment is that it doesn't require you to know what's going on about the variance of the error term. You can remain totally agnostic. Just think, I think it's going to be there, but I'm not sure. I think there is heteroscedasticity, but I have no idea of the form, and I might not have enough evidence to guess. So I'm going to use a formula which is valid whether errors are homoscedastic or heteroscedastic. Homoscedasticity is a problem to think about if you plan to conduct any inference, which means hypothesis testing and building confidence interval. Okay, so let's illustrate that in R. I'm going to take a sample of size 500, doesn't matter. I have the same errors as before, so each error term is going to have a different standard deviation, so it's going to have a different variance. I have the same coefficients as before, beta 0, 1 for the intercept, 2 for the coefficient in front of x, plus my error term. So let's compare. I'm going to start with the standard OLS regression. You can see that my numbers are fairly accurate. 0.9, fairly accurate, it's fairly close to 2. If I get a bigger sample, I would get even more accurate. And 2.01 when the true coefficient is 2. Good. Unbiased, consistent. Very good. However, if I expect that there is heteroscedasticity in the mix, then my standard errors here are simply wrong because R is using the wrong formula. So we can use different functions. If we know the structure of the covariance matrix, I can use this function called GLS, coming from this package NLME, where I regress y on x again, but I'm going to specify how the function is going to be weighted, how x and y are going to be weighted. So I'm going to implement feasible generalized least squares. If I know the variance, I just have to say, well, it's a function, the variance is a function of 2 times x squared. This is what I have in my design here. 2, which is sigma, times x squared. And I can print the summary. Now, my coefficients are still close to 1 and 2 respectively, but my standard errors have changed a lot. I was at 0.13 and 0.129, so pretty much 0.13 across the board with OLS. Now, I am at 0.002 and 0.08, way smaller. The idea is that here, the regression that is being made is the weighted regression. The regression using the weighted variables. So now, I have homoscedasticity again, pretty much. So these standard errors are correct. And I can use them with those coefficients to make confidence intervals and to test any hypothesis. Now, let's say I do not know the variance, but I know the structure. So I suspect that the variance is a power function of the x's, but I don't know what kind of power. It could be power of 2, power of 3, square root is a power, or even minus 2. In this case, I'm going to specify the weights as not exactly the function, because I don't know the true function anymore, but I'm guessing it's a power of x. So I'm going to say it's a form. The form is equal to a power, that's why I have var power, involving x. If I had 3, 4, 5 x's, here I would have to add it's a power of x1 and x3, or x2 and x3, or x1 and x4. And I could put some combinations. What do we have now? Wow, now it's even, the standard errors are even smaller. My two coefficients again are close to their true value. Consistency and unbiasedness are unchanged. Here, you can see that R estimated the power for me. So R tried to estimate the power on the x for the variance. If you remember when I created my epsilon, I made the standard deviation here as a square of x. Well, here, this 2 is what is being estimated here by 1.98. So R consistently estimated the power on the on the standard deviation of my error term. And again, I can use these results to conduct inference, build confidence intervals, and test some hypotheses. Now, let's finish with a more widely used solution. The case where the structure and the actual variance are unknown. So I'm going to use the magic formula coming from White to compute my new standard errors. Interestingly, this function VCOV HAC stands for heteroscedasticity and autocorrelation consistent. This function comes from a package called sandwich. The package is called sandwich because it is made of formulas which consist in adding layers of terms on top of each other. If you remember the OLS formula I showed in the first lecture, there was something called x prime x minus 1 x prime y in matrix form. Well, it turns out that when you do OLS estimations, many formulas have this sandwich form where we have some matrix times a matrix in the middle times the same matrix on the other side. And so there is this idea that there is some meat in the middle and some slices of bread on the sides, which is why the package is called sandwich. We also call this sandwich formulas. So if I look at my initial model, I call my initial model OLS. This whole thing here is what I called OLS. So it's already computed. But then I ask R, okay R, your standard errors here are not good because there is heteroscedasticity. So I want you to give me the modified version, the adjusted formula. And so you can submit your model to this function, VCOV HAC, and then it returns those numbers. This is a variance-covariance matrix. So you need to take the square root of that to obtain the adjusted standard errors. Remember that this is the most widely used solution. You will find many research papers who estimate things by OLS. If they can justify the assumptions, why not? OLS is a great tool. And then they say, well, I'm guessing that there could be some heteroscedasticity of any form going on. Since I do not know the form, the structure, I'm going to adjust my standard errors by using the heteroscedasticity robust formula. And many papers only report OLS estimates and never use GLS or FGLS. Personally, I love GLS and FGLS. I find the method very interesting, but it is harder to justify because each of these methods asks to submit some form for the variance of the error terms. This requires to make more assumptions on top of a lot of assumptions already, whereas this solution just says, no, use this formula. This formula includes any possible form of heteroscedasticity. It even includes the case of homoscedasticity. So this solution is kind of a safe bet. It is commonly accepted in the literature, and this is something you're going to see in most of the papers that will be presented later in the semester. Any questions? Remember that once you get to read your papers, you will have to well, you can always go back to those lecture notes to understand why some methods are used over others, but you will be required to understand all of these, why we use one over the other, what are the potential problems, what are the potential solutions. That's it for this lecture on the extensions of linear models. Have a good rest of your week, and see you in the next one. Bye.